let's work. Now that we understand the difference, we said the limiting reagent is used up in a chemical reaction. So when we say it's used up, what are we saying is that it is it reacts completely. Do you understand?
Yes.
Right. So this means that there is not enough to react with all other reactants. Okay, that's a limiting reagent. And then
Okay.
a reagent which is in excess, it has some moles that will be left over when the reaction has finished. And there are steps that you need to follow when you determine which is the limiting reagent. Number one, very important, always write a balanced equation. When I say always write a balanced equation, this tells you that from this given statement that you see on example 1, we need to write a balanced equation. Number 2, when you have your balanced equation, you're going to calculate the given moles of all the reagents. You understand?
Yes.
Then, when you have the given moles, when you calculate the given moles, you go to step 3. Step 3, very important. This is where you're going to assume one reagent is limited reagent. You're going to assume the given moles of that reagent reacted completely. You're going to choose. Here we have a hydrogen and oxygen. So we're going to choose between hydrogen and oxygen. You choose any to be, you assume that it's a limiting reagent. Okay, then number 3, step 4, you will calculate the number of moles of what? Of the second reagent needed to react with the chosen reagent. I'm not sure if this makes sense. Maybe this will make sense when we work on these examples, right?
Okay.
Right. Let's look at this example 1. We are given 3 moles of H2 and 2 moles of O2 that are mixed, and water is formed. Okay, perfect. Now, before we decide which is the limiting reagent and justify your answer, we need a balanced chemical equation. So I have H2. I don't know. Let me just zoom in. Not zoom out. Maybe. Okay, so we have H2. I'm not sure. Can you see my writing?
Yes, I can.
Okay, so we have H2 that react with what? With oxygen. This is what we have. And they give us water. They say that water is formed. So if water is formed, you need to ask yourself, is this equation balanced? So the equation is only balanced for hydrogen, but not balanced for, it's not balanced for what? It's not balanced
Oxygen.
for the oxygen. So I need to first balance that oxygen. So to balance the oxygen, this tells me that uh, if I put 2 here, then now I have 2 oxygens on the products and I have 2 oxygens on the reactants, but this changes the number of hydrogens because this 2 only applies to the hydrogen. So the hydrogen on the product, there's 2 times 2, which is 4. So to balance the equation completely, we need to put 2 in front of this H2. We need to put 2 in front of that H2. Then the equation is now balanced. I think balancing an equation, that's not an issue for you, né?
Yes.
Perfect. So now you're going to analyze what is going on here. You're going to analyze this looking at the mole ratio. So this tells you that from the mole ratio, we can see that 2 mole of what? 2 mole of H2. In order for the reactions to be complete, it needs 2 mole of H2 needs what? It needs 1 mole of that O2. You can see the mole ratio. I'm not sure if you understand when I say the mole ratio.
I understand.
Perfect. So now, if on the statement they said 3 mole of H2 and 2 mole of O2 are mixed, water is formed. So look at this. I'm going to analyze the statement now. I'm going to analyze the statement. So we can see that from this statement, I'm going to say, oh, shucks. Okay, from this statement, I'm going to say that, can you see they said 3 mole? We were given 3 mole. So 3 mole of what? 3 mole of H2. So 3 mole of H2, it will need what? So the mole ratio, if we have 2 mole, needs 1. This tells you that 3 mole of H2, according to the mole ratio, it will only need, it needs what? 1.5 mole, because half of 3 mole is 1.5. So it will need 1.5 mole of what? Of O2. You understand that part?
Yes.
I'm just looking at the mole ratio because 2:1, it means that oxygen, it will have half of the hydrogen. So that will be half of 3 is 1.5. So now we can conclude. We have 2 moles of what? If you look at this, we have 2 moles of O2. We were given 2 moles of O2, but we only need 1.5. Okay?
Okay.
We have 2 moles of O2. So this tells you that O2 is what? It's in excess. Do you understand that part?
Yes.
Because we only need 2. So we need 1.5, but there's 2 given. So 0.5 will be left out. Therefore, we can conclude and say, therefore, my H2, this is the limiting reagent. Is the limiting reagent. We only have enough H2 to react with what? With 1.5. We have enough H2 to react with 1.5. That one, I think this one, it's easy when you do the mole ratio. Né?
Yes.
Perfect. But in some of the exam questions, they will give you, if you look at this example too, you'll be given examples where you are given the mass, you need to do a lot of calculations, 4-mark questions, 5-mark questions, like this one. 2.8 grams of iron. Another thing, another thing is to understand the molecular formula of an ion. So when I say ion, the molecular of ion, that's Fe. And then of oxygen, the molecular of formula for oxygen, it's O2, because this is a diatomic atom. It's not just O, but O2. Then we know that they are placed in a container, but we need to do a what? We need to draw what we call a balance equation. And then they are heated, and then this forms iron oxide. Do you know what are these 3 lines meaning?
That it's Fe3.
Perfect, not Fe3, nah? Not Fe3, but
Okay.
yeah, the oxide is for the oxide, but don't worry, nah? I forgot what they call this. These 3 lines, I just forgot the name, but this will be it's always, when we say iron oxide, is going to be Fe2O3. Okay, so the 3 is for the oxygen. Okay,
Okay.
when I say iron oxide, just note that I think it's Roman what, but it's fine. Maybe I'll tell you on upcoming lessons if I see this again. I just forgot the name, what we call those 3 lines. So this is what,
Is it Roman numerals?
something like that. Thank you very much. Thank you very much. So now what I'm going to do, I need to first start with the balance equation. So we have Fe, which is iron. Ion is just Fe. It reacts with what? With oxygen, and then the product formed, that's like, this is Fe 2O3. By looking at this, we have a problem here. This equation is not balanced because the products, we have 3 oxygens. The reactants, we have 2 oxygens. The products, we have 2 Fe. On the reactants, we have 1 Fe. So we need to balance the equation. The best way to do this, now, I'm going to give you a shortcut how to do this. You look at the oxygen, look at this 2, and look at this 3. You take that 3, you write it in front of this. You take this 2, you write it here. Then you'll see the oxygen will be balanced. Always start,
Okay.
when you balance equations, if you have oxygen, start with oxygen. If you have hydrogen, start with hydrogen. Always start with those compound. Other one, I think, is carbon, then there's sulfur. Right. So now you can see that now this time we have 4 of Fe, which makes us to put 4 in front of that. Then the equation now, it's balanced. Okay, that's the first step. I said first step, write the balanced equation. Do you still remember the steps that I gave you when we started the lesson?
Yes.
Number 2, I said calculate the given moles of all the reagents. So we need to calculate the moles of Fe and the moles of what? The moles of O2. You calculate the moles of the given reagent. You calculate them. So I'm going to work on that, calculating the moles. I'm going to start with Fe.
I have a question.
Okay, I'm listening.
If it's measured at STP, would you use another formula or?
If there's for the number of moles.
Yeah.
Okay. If they say at STP, ne, you see, I'm going to explain why they say. I'll show you how to attack this one, because I think that's a very good question. There is a reason why they put STP there, ne?
Okay.
And then this is what you're going to do. Ne? If I answer your question now, this might be more complicated, but if I do this first and then answer your question, you'll see why we have why they say measured at STP. So now, if I look at ion, what information do I have about ion? I have the mass. I'm given the mass as 2.8 grams. So if I have the mass and I'm looking for the number of moles, the formula to use is N is equal to the mass over the molar mass. We need the molar mass of Fe, which is something that we can get on the periodic table. And when I look on the periodic table, my Fe, where is it?
Here it's 56. The molar, the 26.
26. Perfect. So the molar mass is the number below, which is 56, right?
Yes.
So I'm going to write 56 here. So this will be 56. Let's write it down here. So the mass is 2.8. This is divided by 56. Therefore, when you punch that on the calculator, you'll get the number of moles of your Fe. What is that equal to? 2.8 divided by 56. What is the answer?
Oh, I put 2.6 by mistake. 0.042.
0.0?
42.
Did you get
424.
for what?
0.0424.
Let me say 2.8 divided by 56.
Oh, I put the wrong amount.
Because what's wrong? Tell me.
I put
0.05.
I put 66 because you wrote down 66, not 56.
No, that's a 5. I'm sorry. It's a 5. But don't do these mistakes in an exam, né?
Okay.
Yeah,
It's 0.05.
0.05 mole. Are you happy with how we calculated the mole of Fe?
Yes.
But now, look at this. For oxygen, we don't have enough information. We just know that the actual moles of A2 for oxygen, and they said it's measured. Oh, they said 2.8 grams of iron. That's the statement and there for iron. Then they and for oxygen, we are given the volume. So the volume is 2 decimeter cube at what? At STP. So remember, at STP, for oxygen, at STP, we know that 22.4 decimeter cube, uh, it's equals to 1 mole. You see, this is at STP. Do you understand that part?
Yes.
Perfect. So I'm going to use this to calculate the number of moles of oxygen. So this tells me that if I'm given 2 decimeter cube, so 2 decimeter cube will be equals to what? It will be equals to 2 over 22.4 mole. Is this making sense? You still remember what we did last time? This is moles at STP.
So, um,
Do you want me to explain this further?
um, yes,
Because
please.
it feels like we have questions, né?
Yes. Why? How did you come to the conclusion that V equals? Wait. Why did you use one more? Why are you using two? Or is it
The
because of
two
the number?
the
Is it
two
because
is
of
for
the
the volume.
coefficient? Yeah.
The two is for the volume, and then 2.24 is for the that volume at STP.
Oh, I'm wondering. Okay, now I see where you got the. So if it says 2 decimeters cubed, then that's the of oxygen. That's the volume.
Exactly. It says and 2 decimeter cube of oxygen. So for oxygen, you take the given volume, which is 2, divided that by what? By the volume at STP, which is 22.4. It's always like this. The answer that you get, it will be the moles of what? Oxygen at STP.
Oh,
But
why didn't you do the same thing for iron?
no, iron we have the mass. We don't have the volume for iron at STP.
Oh, I see.
You understand? We don't have the
Yeah.
volume for iron, but we have the mass. We can find the molar mass and calculate the number of moles.
So are we gonna put the amount we get for? We're gonna put the two amounts into the ratio, the molar ratio, the mole
Okay,
ratio.
let's do this together first. Né? So you're going to say 2 divided by 22.4. Tell me what you get as your answer.
0.0892.
0,089 mole.
Two.
So this is mole of what? This is mole of O2, right? This is the
Yes.
number of moles of O2. So now, uh, listen, listen. First thing first, I want to make sure that you understand uh, how we got to this 0.089. Are you happy with that?
Yes, please.
Okay, so now the next part that you're going to do now, remember I said there are steps that we need to follow. I said the first step, balance the equation. So this was step 1. I said step number 2, calculate the given moles of all the reagent. This was 2. We did 1 and 2. Then step 3, you're going to assume one reagent, it's a limiting reagent. So I'm going to choose any. I'm going to assume that my Fe it's limiting. I'm going to assume that Fe it's a limiting. Okay, so if Fe is a limiting, so I'm going to say that 1 mole, okay, 1 mole of Fe is going to need, it needs a 3/4 mole of what? Mole of O2. Where is this coming from? This is coming from the mole ratio. The mole ratio is 4:3. So if it's 4:3, you just have to say, if I have 4 mole, look at this. If I have, I'm going to erase what I'm going to write now. It's like saying 4 mole of Fe, it needs what? It needs 3 mole of what? Of O2. Then you divide both sides by 4. You divide both sides by 4. The 4 cancel. We left with 1 mole Fe, 1 mole of Fe, which needs that 3/4 mole of O2. So this statement is from the mole ratio. Do you understand that part?
Okay.
Okay.
So would that make O2 um would that make O2 an excess reactant?
We are definitely coming to that part. I just want to erase this part. I just wanted you to understand where is that coming from. The statement 1 mole of Fe needs 3/4 mole of O2. I just wanted you to understand that part. So since you are happy with that, then I can also continue. So now, this is the interesting part. Remember, we said we're going to assume that Fe is limiting. So therefore, I'm going to conclude and say, we're going to compare the amount of O2. I'm going to compare amount of what? Amount of O2. And when you compare the amount of O2, okay, before that, how about we find the moles that are needed? So remember, FOE we said is 0.05 moles. So this tells you that the 0.05 mole of that Fe is going to need what? It's going to need, we're gonna take the 0.05 and then you multiply that 0.05 by what? By 3/4. And this will give us an answer of what? What do you get? 0.05 times 3/4.
0,0375.
375 mole of O2. So this is the number of moles of O2. So you're going to say this is the number of moles of O2. Okay, right. So from that part, now we can definitely compare. So when you compare the mole, you're going to compare amount of O2. And then we're saying that 0.0375 mole of that O2. This will need, it needs what? It needs this guy here. Okay? I'm sorry, not need. This is what we need. Okay? Remember, we first assumed, I don't want to confuse you, we first assumed that F is the limited. So 0.07 mole of O2 is the one that is needed. Okay? But remember, we have what? We have 0.089 mole. Do you still remember that part?
Yes.
Okay, we need 0.037, but we have 0.089. Therefore, can you see that this number here, it's more than the 0,037. So we can therefore conclude and then conclude that O2 is what? O2 is in excess. Is this making sense? And our Fe
Okay.
is indeed
Yes,
a
it makes sense
limiting.
now.
It's indeed limiting. So even if you start assuming that Fe is right, then yeah, just give me a second, okay?
Okay.
Please review these steps. Tell me if you have any questions.
Okay.
Yaki, please, like, please, yeah. Can I watch it? If it is. Okay. Are you good?
I wanted to mention that my teacher taught us a different method where after we found out the moles of each element, then we put them in the mole ratio and do the cross multiplication.
The cross multiplication
Yes.
to calculate the number of moles.
To determine whether or not an element is in excess or limiting.
Are you guys not like calculating the number of moles?
We are as well.
Okay, I
But
think I think I know what you guys are doing. You are using the mole ratio to calculate the number of moles.
yes.
Which is exactly what we did, but I think what you are trying to tell me is that this is how your teacher do. Your teacher is going to say, which in fact, whichever method that you prefer. Ne? So your teacher, what your teacher is saying is that when you have Fe, which is this part, ne?
Yes.
And then I'm not sure if this will work. So we're gonna say Fe is to what? Is to O2, ne? But we know that Fe is 0,05. And then this one is, let's say this one is unknown, it's X. But the mole ratio for Fe, that's 4, is to 3. And then this is 0,05 is to X. So we can use this to find the number of moles of that X. Then you cross multiply. When you cross multiply, you get 4X. It's equals to 3 times 0,05. The answer that you get, you divide both sides by 4. Then what is your X equals to?
It's equal to 0,0375.
0,0375. Then you can compare the mole ratio, but now you're going to have a, okay, so this is how you compare. You can, but remember, you have to follow this step to find this one, right? The mole ratio tells us what we need. We need 0,0375, but what is given? We are given 0,089. You understand? So it's up to you which method you use. I just like to be like more creative. Ne? I'm sorry. But whichever method that you prefer, it's fine. Okay. So when we move to the next lesson, not next lesson, next example. Now this one, I want you to see the difference between all my examples. The first example is where you are given the number of moles for both the reagents. You are given the number of moles for both of them. The second example is when you are given the mass. It's easy to find the number of moles of a certain reagent, but the other one you have to use the STP to find the number of moles. Number 3, you are given this is what has to do with calculating the amount of product from a limiting reagent. Now, when we do this, you're going to identify the limiting reagent, and then you're going to use the number of moles of the limiting reagent and the mole ratio from the balance equation to calculate the product. This is where you use the formula NMCV, what we'll see when we do this example. First thing first, let's read the statement. We have 1 gram of zinc that is put into 250 centimeter cube. I don't like to see that part, because if I don't convert this volume now, I might even forget to do the conversions. It should always be in this meter cube. We divide that guy by 1,000. So this will give us the volume of 0.25 decimeter cube. Are you happy with that part?
Yes.
Then I'm going to separate the given information. We have for zinc, that's Zn. What are you given? The mass, which is 1.3 grams. And then it is put inside. The volume will also work for the zinc. And also, this is what is all for zinc. And then it is put inside of nitric acid. Nitric acid, it's HNO3. HNO3. This is nitric acid, which has a volume of, we converted the volume, that's 0.25. And then we are given the concentration here. The concentration is 0.100 mole per decimeter cube. This will be decimeter cube. Okay, so now with this information that I have, I'm going to first start finding the actual moles for each reagent. The actual moles for each reagent. Number 1, I'm going to start with zinc. I have the mass. It's easy for me to find the number of moles for zinc, and it's small m over big M. Then I do the substitution. So that's 1.3, which is the mass over the molar mass. It's going to be, for zinc, we go to the periodic table. I know that it's somewhere on, what is it? Oh, this shows that I haven't used a periodic table. Okay, so this is 65, né? So I'm going to divide that by 65. You understand? Are you still with me?
Yes.
Hey, I have to confirm, Pella, you'll find maybe I'm busy teaching when now already you are sleeping. So n it's 1.3 over 65. What do you get when you divide these two?
0.02.
0.02 mole of what? Of zinc. Then we are done. For the second one, we need to calculate the number of moles of that nitric acid. But now you look at the given information. You have concentration, you have volume. You need to choose the formula that has C and volume. You remember that formula that says C is equal to N over V. This is the formula that will help us make N subject of the formula. N will be the concentration multiplied by the volume. So the concentration, that's 0.100, multiply that by 0.25. The answer that you get is the number of moles for nitric acid. So this one is for HNO3. So what do you get when you multiply these two terms?
0.025.
So this is 0.025 moles of nitric acid, HNO3. So now you have the number of moles. Remember, when you have the number of moles, we need a balanced chemical equation. I'm going to write down my balanced chemical equation and say that. Okay, so if I write a balanced chemical equation, I'm going to have Z, which is in solid state. This guy react with what? HNO3. And when these two react, they will give us what? They will give us this. I'm not sure if, oh, Jesus Christ. Listen, in an exam, they'll give you the equation. Sometimes it might not be balanced. They'll need you to balance. They won't just give you a statement without an equation. That one we know. So now, since you are going to do acids and base, this is where you're going to understand what we call the, what is this? This is where you're going to understand what we call the, what is this? It's fine. Let me just write the equation, how it will look like. The Zn will be paired with NO3, and then this it's a diatomic. Then we add the H2. Okay, so now which is in this one, it's in aqua solution, and then this one it's a gas. Okay, so I won't focus on writing the state symbols, but now I'll focus on balancing these equations. So now if I have two if I have two hydrogens, I'm forced to put two here, and then also the two here, it balanced everything. So everything is balanced. Né? So I just hope they give you a balanced chemical equation, but you'll definitely get something like this. Né? Don't worry, don't have to stress if you don't understand that part. You'll definitely get that thing. So now, the most important thing is to understand that we said we're going to assume. So I need to assume that one reagent is limiting, and I'll assume that my Zn is limiting. So if Zn is limiting, then looking at the mole ratio, the Zn is 1, the nitric acid is 2. So this tells me that 1 mole of Zn, it needs what? It needs 2 mole of what? Of HNO3 according to the balanced equation. But now we know that for zinc we have 0.02 mole. So 0.02 mole will need what? It will need if I have 0.02 and we say one of this needs double of that, you're gonna say 0.02 times 2, which gives us 0.04. So this is what we need for nitric acid. I'm not sure, are you following?
Yes.
So if this is what we need, look at what we have. We only have what? We only have 0.025 mole of that HNO3. Can you see? That's not, is that enough? That's not enough. You understand? This
Yes.
is what we need, but we have less of that. This tells us that we're going to conclude what we assumed is wrong. Then we conclude and say, therefore, our HNO3 is the one that is a limiting, is the one that will run out first, is the one that is a limiting reagent. So whatever that we assumed, it's wrong. You can assume anything, it's up to you. You'll find the correct answer at the end. Do you understand how this works?
Yes.
Okay, so the next question wants us to, it wants us to calculate the volume at STP of hydrogen gas produced in the reaction. So you're going to write your H2 down. H2, hydrogen gas. So when we need, they want us to find the volume of hydrogen gas, and I'm going to do an information. Né? So let's do a data so that we can understand what is going on here, or maybe you want me to start by telling you what we need. This is at STP. Don't worry, I'll take this step by step. So now, to answer this question, when they want you to find the volume at STP, calculate the volume at STP of hydrogen gas. Oh, Jesus. Okay, I'm going to say for, let me not start with H2. Let me just go to the balanced equation. We set the number of moles for, we had Zn, which reacted with 2HNO3, and this gives us Z into NO3 2, and then plus H2. So now we are looking for the V question mark for hydrogen gas. And then now the mole ratio for this one is 1. So I'm just going to choose between these two. Which one am I going to compare it with H2? You can choose any one, and I'll go with what? I'll go with the nitric acid. So for the nitric acid, the mole ratio is 2. So the mole ratio is 2:1, but we calculated the number of moles of nitric acid as 0.025. So I'm going to say the number of moles here, and it's equal to 0.025 mole. That is the number of moles. So this is a very important information that we need to use to find the number of moles for that H2. Do you understand?
Yes.
So if nitric acid is twice what? If nitric acid is twice H2, therefore I'm going to conclude and say the number of moles of H2 will be half of that. So it will be 1/2 multiplying 0.025. That is the number of moles of H2. Then when you punch this on the calculator, what do you get? What is half of 0.025?
0.0125.
125 mole of what? Of H2. So this is the number of moles of H2, which is also important for the next part. I'm just going to put it in a block so that we're trying to highlight this. So now, this is what I have so far. And if I go back to the statement, they said that calculate the volume at STP for hydrogen gas. That's what we need. We just need the number of moles. Remember, 1 mole of what? 1 mole of H2 is going to occupy what? 22.4 decimeter cube volume at STP. Do you still remember that?
Yes.
Even on top, we said 1 mole of 22 decimeter. We said that 22 decimeter for any molecule, it will occupy 1 mole. So if I have 1 mole of H2 that occupies 22, this tells you that at STP, we have what? We have 0.0125, right? So 0.0125 mole of H2, it will occupy what? It will occupy, you take that 0.0125, you're going to multiply that by 22.4 decimeter cube. The answer that you get is the volume that we are looking for.
Okay.
Then what is the volume of H2?
0.28.
0.28, that's your answer. 0.28. So the volume of H2, that is 0.28 decimeter cube. Okay, so now I'm just going to give you some time
Okay.
to work on the final answer. Let's see what you get, because you have this example that I need you to work on. I'm just going to give you time. And then there's also homework with selected question. I am looking forward to mark the work. When you are done, you'll email me your solution. You know, another thing that I'm going to tell you. So there is a reason why I'm choosing this. But for now, I'm just going to pause the lesson here, give you time to work on this example, and this will be let me just check, this will be the last example of this lesson, but we still, remember I said we'll do 1 hour 30 minutes.
Yes.
Yeah, so I'm just going to give you some time. If you can work this within 15 minutes, the remaining 15 minutes, I'm just going to explain the solution of this example 4, okay?
Okay.
Perfect.